Good morning, and you're very welcome to this morning's webinar. My name is Mark Gibson, and I'm Program Manager of Teagasc Connected. Wherever you are today, I hope you're getting a chance to enjoy this fine weather and that you're keeping safe and well during these extraordinary times. This is the third in our series of Teagasc Connected Signpost webinars, which examine the science, policy and advice around farm sustainability in Ireland. The series is delivered in association with the National Rural Network, Dairy Sustainability Ireland, and Food Drink Ireland SkillNet. We want this session to be as interactive as possible. You'll see at the bottom of your screen a Q&A tab. I encourage you to make the most of this function. Simply type in your question and hit submit, and we will endeavour to put your questions and comments to the speaker at the end of our session. Also, just to note that today's session is being recorded and will be available to view afterwards on the Teagasc YouTube channel, and also the speaker's presentation will be available on the Teagasc website. The Teagasc Marginal Abatement Cost Curve, also known as the MAC, is central to Ireland's strategy to reducing gaseous emissions from agriculture. To explain the science that underpins the MAC, I'm delighted to be joined by Professor Gary Lanigan, who leads the Gaseous Emission Research Group at Teagasc Johnstown Castle. He is a member of the UN Expert Panel on the Mitigation of Agricultural Nitrogen and is an advisor to the EPA's Climate Change Research Programme. Gary, you're very welcome to our programme today.
Thank you very much, Mark.
Gary, I'm just going to switch to your video there and we should be able to see you. Okay. So, Gary, you're going to give us a 25-minute presentation on the latest developments on gaseous emissions. If I could hand over to you, Gary, and hope everything runs smoothly for us today.
Okay, thank you very much, Mark. What I'm talking about today is Teagasc's Marginal Abatement Cost Curve. And basically, for those of you that don't know it, it is merely a marginal abatement cost curve is really just a way to rank measures. Okay, so what we've done is we've looked at the 28 most likely measures that we can use to reduce greenhouse gas emissions and also reduce ammonia emissions. And what we've done is ranked them both in terms of the amount of mitigation they can do and also the costings of those measures. Okay, so it's essentially a cost-benefit analysis. Okay. You would have heard any of those of you that have been at the other series of lectures on this by John Muldowney et al. That agriculture really has a number of different challenges facing it at the moment. First of all, the industry is expanding to meet global food demand. The FAO predict that there will be a sustained demand for dairy and meat products over the next coming years up to 2050, okay, as population grows and also as populations in developing countries become more wealthy. On top of this, not only do we have, does industry have an expectation to increase both in terms of value and in terms of volume, as been laid down by, first of all, Food Harvest and then Foodwise 2030. We also have to reduce our greenhouse gas and ammonia emissions. So unlike, we're a real outlier in terms of the EU. Most EU countries, about 9 to 10% of their greenhouse gas emissions are from agriculture. A third of our greenhouse gas emissions stem from agriculture, and 98%, virtually all our ammonia emissions, also arise from agriculture. Okay, and this is twofold. First of all, we don't have a whole lot of heavy industry to dilute our agricultural emissions, unlike other EU countries. And also we have a preponderance of livestock. So our greenhouse gas emissions are dominated by methane from ruminants from enteric fermentation and nitrous oxide arising from animals urinating and defecating on pasture, and also from fertilizer application. And in terms of our agricultural targets, so we have our food-wise and food harvest production targets, but we also have agricultural 2030 targets. So under the government's climate action plan, we have to reduce greenhouse gas emissions from agriculture by 10%. And for the wider economy, as part of the EU's 2030 targets, we need to reduce our greenhouse gas emissions from the entire state by 30% by 2030. So this is quite an onerous target, particularly because we're actually already behind the curve. So we narrowly missed our 2020 target, so we're already playing catch up for our 2030 targets. And just to bear in mind that the 2030 targets are a multi-year target. So you don't do all your mitigation in 2030, you have to have ongoing mitigation between 2020 and 2030. So we have challenges both in terms of reducing emissions and also in trying to deliver carbon sequestration to offset emissions, which I'll come back to later. In terms of our ammonia targets, we're already in breach of our ammonia ceilings under the National Emissions Ceiling Directive. We have a 1% reduction target from 2020 to 2030 and 5% from 2030 onwards. So in this context, what you're going to find is that there will be increasing political pressure on agriculture to reduce its environmental impact, and particularly as other parts of the economy decarbonize, such as transport, residential emissions, etc. What you will find is that a larger proportion of the residual emissions left behind will probably derive from the agriculture and land use sectors. Okay, but again, there is increasing political pressure, both in terms of the EU's Green Deal, an increasing emphasis on plant-based diets, planning permissions up in Northern Ireland being refused due to ammonia emissions. So there's an environmental context which is gathering pace really with this. And ultimately, the government hopes to achieve carbon neutrality is our long-term goal, carbon neutrality for the whole of the state by 2050. Okay, so if you're going to run a marginal abatement cost curve and you're going to try and project what happens with agriculture into the future, the first thing we have to do is project what agricultural activity will be like. Okay, and we basically had 3 scenarios. So the S1, which was our soft Brexit baseline scenario, the S2, which was a hard Brexit low activity scenario, and S3, which is a high activity scenario. So basically the difference between these 3 scenarios is that for the top scenario, there's about 1.8 million dairy cows, 1.6 million dairy cows in the bottom scenario, and the suckler herd then has different sizes with all of these 3. So the S2 hard Brexit scenario would see about a halving of the suckler herd. The S1, slightly lower number of suckler animals, about 800,000 than we currently have, and S3 would see no real decrease in suckler herd. Okay, so under these 3 scenarios, and concomitant with this, there's also then increases in fertilizer usage as you have increases in herd size and the size of the national herd. And what you see because of this increase in animal numbers or change in animal numbers for the different scenarios, you see 3 very different trajectories of what our baseline figures might be under the S1, S2, and S3 scenarios. So you're looking at a spread of somewhere just short of 2 million tonnes between the top and the bottom scenario. And just to show where we need to be under the Climate Action Plan somewhere between 17.5 and 19 million tonnes. Okay. So if we look at our ammonia emissions, then again we also see a consequence of those different levels of activity in the projections on our ammonia emissions. And just to show where we need to be, the 112.2 is our 2020 to 2030 target, and the 107.7 tonnes is our 2030 5% reduction target. Okay, so as you can see, particularly if we're following close to the S3 high activity scenario, we've a lot of ground to make up.
Gary, can I just clarify that those scenarios are without any mitigation?
They're without any mitigation. They are business as usual scenarios without any mitigation. Correct.
Thanks.
So if we then look at what is a MAC, a marginal abatement cost curve? Well, simply it's a graph that ranks your measures. Okay, the width of the bar indicates the abatement potential of an individual measure. So the wider the bar, the more effective it is at reducing either greenhouse gases or ammonia. The bar height indicates the cost. So negative values, everything below the line indicates a cost saving, whereas everything above the line is an actual cost. So the taller the bars, the more expensive they are. Okay, and then the hatched line across signifies the mean cost of abatement on a greenhouse gas, ton of greenhouse gas abated or ton of ammonia abated. Okay, so that's a quick explanation as to the actual graphs. So if we look at the solutions that we looked at, first of all, our strategy was to reduce methane by efficiency measures. That was utilize measures that would reduce the carbon footprint of a litre of milk or a kilo of beef. And that was mainly around things like animal genetics, finishing times, optimizing output per head, extended grazing, improved animal health, and also some dietary changes. The second set of our strategies was around nitrogen, okay, and nutrient use. And really that focuses on two things. First of all, reducing nitrogen input as much as possible. That's by improving nitrogen use efficiency, either through appropriate liming and appropriate good soil status, and also by the use of clover, but also by changing fertilizer formulation. Okay, so really reduce nitrogen where possible, and if you can't reduce the amount of mineral nitrogen, change the type of mineral nitrogen you apply. Also, we had strategies on manure, so putting in additives that can reduce ammonia and methane, and also by applying your slurry with a low emission slurry spreading technique that will A, reduce greenhouse gas and ammonia emissions, and B, will improve the nitrogen fertilizer replacement value of your slurry, which in turn means you then need to apply less mineral fertilizer. Okay, but concomitant with all of these solutions that I'm going to show you now is the underlying need for effective knowledge transfer. Unless we get effective knowledge transfer, then all these mitigation options that are laid out in the MAC are merely notional. Okay, so if we look at agricultural mitigation, what we see is the main options that are most effective are dairy EBI, so improving the genetic merit of the dairy herd, changing fertilizer type, you see is a nice wide bar as well, and also the use of things like low emission spreading, slurry amendments, animal health, extended grazing, okay, changes in reducing crude protein in pig diets, the use of clover, and here the use of lime to improve nitrogen use efficiency and soil nutrient cycling. So basically, when we crunched all these together, what we came up with was that assuming linear uptake of these measures over the 10-year period, that you would be able to mitigate slightly under 2 million tons, 1.85 million tons. And by 2030, we would be reaching a maximum mitigation of 3 million tons per year. And that's assuming that we get good uptake in a lot of these measures. So for example, we're assuming that we could apply clover to 20% of beef farms at least, and 15% of dairy farms. For nitrogen use efficiency, about a third of our soils are not at the right pH. And so if we can get half of those soils back up to optimal pH, what you do then is you're saving about 70 kilos of nitrogen per hectare per year simply by having your soil at the appropriate pH level. The two biggest measures are dairy EBI and the fertilizer type, which I'll come on to in a minute. The one thing I will say, and I'll just give a little bit of warning about some of these efficiency measures, is that the savings in terms of greenhouse gases are notional, particularly if you have a rising animal population. What these measures do is they dampen the amount of greenhouse gases per animal or per head for every extra animal you have, but they won't eliminate them. And in fact, if some of these measures like dairy EBI and some of the beef measures are profitable, you can end up with a rebound effect, whereas as your farm becomes more profitable, you end up having more activity and your greenhouse gas emissions can in fact go up, okay? So that's just a health warning with those measures. So rather than show it fully on a graphical format, I've tabulated out the main winners here in terms of the measures that we have. So protected urea, dairy EBI, low emission slurry spreading, draining wet mineral soils. These are all measures that are quite effective, and in particular, the low emission slurry spreading is also very effective over here in terms of ammonia measures. In fact, amongst the ammonia measures, moving to low emission spreading and protected urea make up the vast bulk of the mitigation actions that we can do. So they are really no-brainers in terms of mitigation measures. And we also have two other different types of MACs as well. So we looked at agricultural measures, but we also looked at land use change in forestry. So these are, instead of reducing emissions, we're offsetting emissions by sucking up more CO2 out of the atmosphere. And really, the big options here are forestry, water table management of organic soils. So these are organic soils that are in agricultural production that have probably previously been arterially drained in the 60s and 70s and 80s. And some of those drains might already be stopped up, but some of them we might want to re-wet. Pasture management and tillage management then makes up the rest of this carbon sequestration tranche of emissions and emission savings. And then finally, we have the bioenergy measures, which the savings don't necessarily accrue to the agricultural sector, but agriculture is still contributing to the decarbonisation of the wider Irish economy. So really here, it's the likes of wood biomass for energy, biogas, and biomethane that are going to offer the the biggest savings. Okay.
Gary, just had a quick question there. Just maybe you could explain what EBI is for some of the viewers.
Okay. So the dairy EBI is the Economic Breeding Index, and really what it is it's an index of the amount of the value of your dairy system and your dairy cow per greenhouse gas emissions produced. So really what the EBI is doing is selecting for higher genetic merit animals on the dairy side and on the beef side as well with the Beef Quality Assurance Scheme. So basically it's an index that incentivizes either a higher amount of milk per head or a lower need for replacement animals. Perfect. So it's an index. It's an economic index of dairy milk production.
And Gary, we have one more question here. SRC, just a quick definition of that.
SRC is short rotation coppicing. So that's the use of willow primarily for burning for either heat production or electricity production in a combined heat and power plant.
Okay, perfect. Thanks, Gary.
Okay, so I'm going to focus in on a couple of these measures, and the big measure across both the ammonia side of things and the greenhouse gas side of things is actually optimizing your farm nitrogen use, okay, and minimizing the use of chemical nitrogen fertilizer where appropriate, okay. And this is a slide from Patrick Forrestal, and basically what it shows is why fertilizer formulation is an important strategy for us to look at, okay. So what you see is that ammonia emissions from unprotected urea are much higher than for CAN or protected urea. But in terms of greenhouse gases, you can see that nitrous oxide emissions are highest for calcium ammonium nitrate compared to protected urea and unprotected urea. Okay, so what does this tell us? First of all, where possible, to reduce the amount of nitrogen being used. Okay, and how will that happen? Well, by moving to, for example, low slurry spreading techniques, you will save a certain amount of nitrogen that will go up into the air. If you splash plate apply slurry, you can lose between 50 and 90% of the nitrogen in that slurry. So by moving to a low emissions technique, you're going to be saving maybe, you know, an extra 30 to 40% of that slurry nitrogen that would have disappeared off into the atmosphere. The use of clover, if done judiciously, again, will probably offset the need for nitrogen by about 70 to 80 kilos of nitrogen per hectare per year. And also then good management of your soils in terms of liming and in terms of your P status will then reduce your need for nitrogen. So again, in soils, if you bring soil up from pH 5.5 to 6.8, you basically can release about 70 kilos of nitrogen and 2.5 kilos of phosphorus per hectare per year. Okay, so you then reduce the need, but what we need to see is on farms actual reductions then in the amount of mineral fertilizer being put on when we use these techniques. There's no point, for example, going and using a trailing shoe or a trailing hose machine for slurry spreading and then still putting on the same amount of mineral nitrogen that was being put on before. Okay, so we have to manage our nitrogen use, and where we can't manage our nitrogen use, then we need to think about changing over particularly from unprotected urea to protected urea in the first instance, because that's a huge saving for us on our ammonia emissions. And then subsequent to that, moving some of our calcium ammonium nitrate to protected urea in order to reduce our nitrous oxide emissions. Okay, the next bit I'll come to is forestry and land use. So under the flexibilities that we have afforded in the EU 2030 targets, we can bank just under 27 million tonnes. That's 2.68 million tonnes per year by enhancing what's called carbon sinks, okay? And that is basically sucking up CO2 and locking it either A, in the soil, or B, in woody biomass, be it in trees or in hedgerows. And Ireland were given quite a generous flexibility under this plan, but there is actually huge scope for Ireland to actually elect more sequestration, particularly both in the forestry section and the organic soil section, but also in grasslands and in croplands. And just one word of warning as I carry on. Our forestry sink, which currently is contributing just over 2 million tonnes of mitigation, won't last forever unless we get our planting rates up. So these are model runs using a model called Carbware. And what this shows is that for different planting rates, you have a different size of a sink, okay? But the thing to notice is that under the lowest planting rate, 3,500 hectares per year, which is roughly what the planting rate is at the moment, that our carbon sink in forestry falls off a cliff somewhere just after 2030. And that's simply because our rate of deforestation at some point will overtake our rate of afforestation. And that's because we actually planted a lot of our forestry between 1990 and 2000 or so. So that cohort of tree stands are coming towards maturity around about in the next 10 years or so. Okay.
Gary, I just have a question here. It came in. I thought it might be a good time to ask it. It's asked here, is there a crossover between forestry and wood biomass? Are the figures including biomass production from forestry separate? Or if separate, what area of biomass would be needed to deliver 0.76 megatons of CO2 equivalents?
So the woody biomass for heat production is really things like sawdust and thinnings from our current stock. However, there is a difference in that our miscanthus and short rotation coppicing figures are separate to forestry. So they're separate.
Okay.
I just want to spend a couple of minutes explaining carbon sequestration here, because it is something that's quite misunderstood, I think. So when we talk about carbon sequestration, like I said, that can either be carbon locked in trees, in woody biomass and in hedgerows, or in soils, okay? And the amount of carbon in soils is influenced really by two different things. First of all, the type of soil that you have. So a light soil will have a very small sink, okay? So it will have a much smaller capacity to lock in carbon. And if you have a crop on that, because that crop is highly disturbed and also there's a fallow period, you have a lot of CO2 being taken up by that crop, but you also have a lot of CO2 leaving the system. So in cropland situations, we tend to see carbon in general leaving those systems. If we take a clay soil, which has a larger sink and a larger capacity to bind carbon to it, that has a larger capacity to bind carbon. And what you would find then in a grassland, for example, So grassland as well has high CO2 uptake. And the more efficiently you grow your grass, so anything that makes you improve your yield should, in theory, also improve your soil carbon sequestration. So what you see is that the uptake is high, and because though it's a permanent system, the losses tend to be lower. So there's less respiration, less decomposition in these systems. So you get your carbon levels going up in grasslands. And then we have peat soils. And for this purpose, I have the carbon sink as a swimming pool compared to a basin. So in tillage soil, you typically get values of about 80 to 100 tons of carbon per hectare. In a peat soil, it's more 700 to 1,000 tons of carbon per hectare. So these peat soils, in fact, have been described as our rainforests because there is a huge amount of carbon, 1,000 tons of carbon per hectare locked away in these soils. And these soils have low CO2 uptake, but it's like a sink with a plug in, nothing really leaves it. So they are really the soils that we have to focus on maintaining carbon stocks. And another thing just to mention is that carbon sequestration is finite, okay? So you go from one land use, say a cropland to a grassland, and eventually your carbon levels will top out, okay? It is also reversible. And the rule of thumb is that you lose carbon 6 times quicker than you gain it back, okay? And then we come to the issue about how it's counted. So people go on or talk a lot about us being able to count our grassland sequestration, okay? But the problem is that we cannot count all that sequestration because what you have is you have this period here before our baseline year, 2005 is when all our measurements are based against. So we have to prove a management change in our grasslands between, say, 2005 and now in order to and it's this additional sequestration caused by the management change that we can count as grassland carbon sequestration. The amount that's been going on in perpetuity cannot be counted because it's all been going on. And this is just a slide to show that issue that as you convert a grassland to a cropland, you lose soil carbon very quickly, but when you convert a cropland back to a grassland, it only slowly recovers its soil carbon. And then we come to re-wetting of drained peatlands, which is another one of our options. And really, this is these are huge hotspots of emissions. Where you drain peat soils and you introduce air into those soils, and like I said, those soils have 700 to 1,000 tons of carbon per hectare. You emit somewhere between 16 and 30 tons of CO2 per hectare per year. So we've calculated that re-wetting 40,000 hectares of this will offset just under 500,000 tons of CO2 per year. So a relatively small area that would need to be re-wetted for quite a large offset. But ultimately, all these measures that are in the MAC curve are notional at best unless we can get implementation on the ground. So we need to see implementation of good soil nutrient practice, of low emission spreading technologies, of improving the genetic merit and the health of our bovines, reducing the crude protein content of our pig diets, changing how our attitude to nitrogen fertilizer, and improving, reducing our farm end surpluses. And then also really looking at landscape solutions So can we plant a row of trees that might intercept ammonia or intercept nitrate going down to a watercourse, and those trees as well will capture carbon and improve carbon sequestration. So we need a real renewal of the link between research, advisory, and on-the-ground implementation of these measures. Because without on-the-ground implementation of the measures, we will not reach any of our targets. So, advisory is absolutely key.
Gary, we have a question here from somebody who's asking, is there a simple tool developed for farms to evaluate their emission levels based on their practices?
Okay, so we have a carbon navigator that will be getting overhauled. So in the first instance, I would say the carbon navigator. Ultimately, I think the way ahead for us is going to be to have have pasture base and NMP online needs to link into a carbon accounting tool, be it the carbon navigator or something else, and that then ultimately would be the on-farm tool that farmers would use. So in the first instance, yes, we do have the carbon navigator, and hopefully we'll be overhauling that fairly soon. So in summary, we have a lot of challenges. We have targets both in terms of greenhouse gas emissions and ammonia emissions. The CAP has, of course, increased environmental focus, and there is increased environmental regulation, both EU and national, coming on stream. Okay. There's also going to be challenges in the future with price volatility. We've got challenges at the moment with COVID and probably with Brexit coming down the line, which is going to introduce a level of economic uncertainty in the short to medium term, and also society's expectation for the stewardship and management of the land is changing as well. Significant mitigation potential exists. That's my final take-home point, but these only exist at the moment on paper. There's significant advisory, communication, and action required by all of the stakeholders across the entire farm to fork value chain. Okay, so this is needs a joint effort from scientists, from advisors, from farmers, and also from industry, and particularly the focus really for most of the MAC measures is at farm level to reduce these emissions, and behavioural change, again, particularly in relation to land use, land management, and also soil husbandry and nitrogen husbandry needs to change in a significant way. And finally, we do then also need diversification and land use optimization. So again, instead of just thinking of these things on a field basis or a farm basis, we need to actually think of a lot of these solutions on a landscape basis. Okay, so it's not necessarily, for example, a forestry plantation. There might be a little bit of agroforestry or a line of trees or different options that fit into the context of where you are on the landscape. Are you near a watercourse, for example, or are you on a hillside or whatever? But again, we do need good land use optimization to put the appropriate land management and land use in the appropriate place. And ultimately, we need to have integrated sustainability measures that also incorporate water quality and biodiversity, because there's no use in fixing one problem and making another problem worse. Okay, and probably the obvious example of that would be while Sitka spruce, for example, is good at sequestering carbon. It's not necessarily ideal for biodiversity, and or water quality, depending on where it's put. So we do also have to keep in mind these other environmental criterion when we're drawing up sustainability measures. And that's it. Thank you very much.
That's great, Gary. Thank you very much for that. And that's a really good point to finish on. I mean, we really do have to keep an eye on all of the environmental indicators, water quality, soils, biodiversity, and it is a bit of a juggling act, really, isn't it? We have to be careful about what the consequences of some of our measures on looking after the various headings.
Yes, absolutely.
So what we'll do is we might just, with lots and lots of questions, Gary. So what we'll do is we'll try and get through as many questions as possible. So if I could ask you to maybe try and be as concise as possible with your answers, if possible. I know, look, this is a complex area, so so there should be a few fairly quick ones. But I mean, there was a general question there that was asked there about the Kyoto Protocol. Is this the best and only option available to Ireland? It's, you know. Well,
yeah, we've kind of gone beyond the Kyoto Protocol. So the Kyoto Protocol in its first iteration ran up to 2012, and then the iterations since then have essentially been EU level. So we had our 20% reduction by 2020 targets, and now our 30% reduction by 2030. So they're the only option in town at the moment. You know, there are EU directives, we've signed up to them, you know, so we have to meet them in some way. We're obliged to.
Okay. Do you think that in the next few years that the targets for agriculture might be increased to values of 30% or more, similar to what other sectors are being asked to do?
I would imagine, well, they're not going to go down, let's put it that way. So I think it's inevitable that they're only going to get more onerous. At what level they might cap out at is a movable feast, but inevitably they will get much more onerous, yes.
Okay, very good. What would the impact of speeding up the adoption rate of measures like protected urea on the total amount of abatement between 2020 and 2030, i.e. the maximum abatement potential?
Yeah, okay. So basically, if you look at all the measures together, if you assume linear uptake, we were estimating 1.85 million tons. That was the average mitigation per year, assuming linear uptake. Were you to magically be able to implement all those measures at their full adoption rate immediately, it'd be 3 million tons per year. Okay. Now, some of those measures you can't front end, things like improving the genetic merit of the dairy herd, for example. That's a gradual thing. But some of the other measures, like as you said, the fertilizer type, you could front end that. Okay, and certainly I think we envisage certainly for ammonia emissions, we would say, front ending the replacement of unprotected urea with protected urea seems a sensible enough option to quickly reduce emissions.
Okay, another question here. All of these measures come with requiring a greater level of management ability at a farm level. Do you think the farming community is able to, firstly, cope with the cost of these management changes, and secondly, the decision-making skills to undertake them?
I think it depends on the measure, but I think, yes, you're right to a certain degree, particularly things like appropriate, keeping your soil at an appropriate pH, and the introduction of clover, absolutely, it takes an increase in management skills. no doubt. So in general, I would say yes, there's an educational piece in there for a lot of the measures, and certainly an advisory piece for all of the measures.
Mm-hmm. Gary, we have a question in relation to organic farming and its impact on greenhouse gas emissions. I mean, how does organic farming compare with say, conventional farming in terms of its emissions? I know there's a emissions per unit of product versus per hectare issue there, I imagine.
There is. Okay, so basically on the total absolute emissions from an organic farm will be lower than from, say, a conventional farm with the same number of cows, etc. What you tend to see is there tends to be slightly more methane coming from those animals because there tends to be higher roughage in the diet. But also there tends to be, don't forget carbon, your carbon footprint is your numerator, your emissions over the amount of product you produce. So what tends to happen on organic farms is they've lower emissions, but they've also got a lower amount of product. So their carbon footprint doesn't necessarily get better, but their absolute emissions, yes, are low, would tend to be lower than a conventional farm, because again, they're not putting on mineral fertilizer. And mineral fertilizer application probably accounts for about a quarter of the carbon footprint of that farm.
We've had quite a few questions, Gary, in relation to the Carbon Navigator, and some people are wondering where it can be accessed. I mean, it is a part of the service. I work with the advisory services and knowledge transfer section in Teagasc, but it is a tool available through agricultural advisors, private and public. It's a collaborative tool, or a tool developed in collaboration with Board Via. Now, there was a question, Gary, in relation to the Carbon Navigator as to whether carbon sequestration was included in that. The current version, I don't think it is it?
No, there is a small amount of carbon sequestration included in it, but not really. That's why I was saying we do need an overhaul of the Carbon Navigator to be able to introduce sequestration measures in.
Okay. A few questions, Gary, in relation to minimum tillage. Can Gary expand on the carbon losses associated with different methods of reseeding grasslands, full till versus min till or direct till methods?
Okay. So what we tend to see is that in minimum tillage systems, you tend to have slightly more soil organic carbon in the top, in that plough layer, which it might be, about 10 centimeters deep. We don't tend to see, certainly for reseeding of grasslands, we don't tend to see a large amount of carbon loss for ploughing versus min-till. You don't really see it, not for an occasional reseeding of grassland. If you're seeding, say, once every 10 years, the actual amount of carbon lost by ploughing relative to min-till would be fairly minimal. What you tend to see in min-till systems is you have you've got greater aggregate formation. So the amount of protected carbon in min-till systems tends to be higher than in conventionally ploughed systems. But the difference doesn't in total carbon stocks between min-till and normal moldboard ploughing doesn't tend to be as great as we think.
Okay, bring it down to field level, Gary. If you have a wet field that is covered in rushes,
yes,
let's say 3 acres, and drainage has failed in the past, would it be more beneficial to plant it with forestry or agroforestry, or would it sequester more left as is?
It would depend on the soil type you were on, is the answer to that one, Mark. So if it's a wet mineral soil, then by all means, go ahead and put a bit of forestry on it. If it's a peat soil, I wouldn't go. I would leave the drains stopped up.
Is there, Gary, is there any, I know from speaking to other people in the policy side of this area, that EBI is currently not considered as part of the inventory. Is that still the case, or is it going
no,
away in the
it's
future?
not. So no, it's not. And the way we get at the reductions in EBI is what we do is we run our greenhouse gas models with animals with a lower EBI, then run it with animals with a higher EBI. And what happens is you need less animals to produce your milk target. Yeah, so that's how it works. So the way EBI and a lot of the efficiency measures work is they don't really work by, they avoid emissions by needing less cows to meet your milk production target. So what it does is it dampens the amount of emissions associated with that level of milk production.
We saw in John Muldowney's presentation last week that there was actually a very strong downward trajectory of emissions up until I suppose the quota was removed.
Yes.
And John was saying that a lot of that can be attributed to those efficiency gains.
Yes. So again, the reductions that we saw prior to 2014, well, up to about 2011, 2012, were probably a mixture of improved efficiency on the dairy side, reduction in sheep numbers, and also quite a significant reduction in fertilizer usage over the period from 1998 to about 2011. We saw about a 30% reduction in nitrogen use over that period. So they would have been the main drivers of that decrease. And the main causes of the increase since then are increased dairy numbers and an increased fertilizer usage.
Are there any incentives for farmers to re-wet peaty soils? I think at the moment.
At the moment, not that I know of, but certainly it is something that should be incentivized. I think, as I said, these are our rainforests and they should be treated as such. So they should be maintained. The carbon stocks in them are so high that they need to be maintained and preserved as best possible.
Is adaptive variation owing to a plant's response to changing climatic conditions and/or increasing impact of disease owing to rising temperatures likely to significantly influence our CO2 sequestration? There's a technical question for you.
Yes. So actually, we had a paper out on this a few years back, where we did see that under rising temperature conditions, that it could adversely impact on our ability to sequester carbon, because the relationship between soil temperature and CO2 emissions from soil are exponentially related to each other. On the other hand, as the CO2 levels increase, you also increase the water use efficiency of your plants. So they tend to become slightly more drought resistant because the pores that open up to let water out and let CO2 in, they don't need to have as many of them. So you sometimes, depending on, you get a little bump in yield from the higher CO2 levels. So it's what we call CO2 fertilization effect. But that's very, very dependent on species, etc. So some crops respond well to increased CO2. Some of them don't respond at all. But they will all respond to elevated temperatures. And what we've seen in drought situations, because we have equipment that measures the carbon balance on a field scale, is we see our grassland sinks flip and become sources of carbon. So the carbon leaving the system in drought situations is higher than the amount of carbon coming into the system, which makes sense because like when we had our last drought situation a couple of years ago, we had very little grass growth. You have very little grass growth, you have no sequestration.
Gary, there's a question here in relation to the role of the consumer, and this is an area that we've talked about before. That, you know, that a lot of we know that a lot of greenhouse gas emissions are driven by the consumer ultimately. So the question here is, how can we link farm rewarding to consumer purchasing? Or could this be done through a form of farm certification, which would influence consumer buying behavior? Or maybe you've seen other schemes from other countries, Gary. I'm not sure. Have you seen what work's going on in this area?
So it was actually a large part of the IPCC's special report on land and climate change. So what we tend to see is that if you look at the kind of farm fork emissions associated with the production of anything, any commodity from agriculture, what we tend to see is that about 30% of the emissions are associated with food waste, as in, and that could be food waste across the whole chain. So it could be food, it could be wastage at the farm level, it could be wastage at the retailer level where they throw out food, or it can be wastage at the consumer level where they buy food, and that seems to be, no matter where you go across the globe, somewhere around about 30%. So it's quite high. What I would say, the problem we probably have with demand side measures is that we export most of what we produce. So it's not our behavior that needs to be changed. So we can change our behavior in this country, and that will have a certain amount of an effect. But about 80 to 90% of what we're producing is going abroad. So it's somebody else's behavior we need to change. How you do that multilaterally is difficult. I mean, World Health Organization, the FAO, do have kind of blueprints for healthy diets and this sort of thing, and demetarian diets where you eat less meat. But really, in terms of having an impact on our emissions, you're really talking about other countries' emission profile, not or other countries' behaviors. Okay, it's consumers aren't, most of them aren't in this country that are eating the produce.
That's a fair point. Gary, we're getting a lot of questions around protected urea, and there's some mixed, I suppose, understanding around protected urea. Can you, and this will be our final question, can you just give us some clarity around the concerns that have been raised around protected urea?
Okay, so what we define as protected urea is urea that has been coated with a chemical called MBPT, okay, or agrotane, which is its trademark name. The product we worked very well in a grassland context. In a cropland context, we didn't see any differences between protected urea and calcium ammonium nitrate in terms of nitrous oxide, and that's because on most croplands, nitrous oxide emissions tend to be very low anyway, and that's a consequence of them having low carbon stocks. They tend to be on sandier, more free draining soil, so there tends to be not very much nitrous oxide associated with fertilizer application to croplands. However, on grasslands, the product that we used was extremely effective at reducing nitrous oxide emissions, and has much lower ammonia emissions. So it behaves much more like a canned product than a urea product. Again, there are density and spreading issues around it, which is why in a cropland situation where you have quite large bout widths, we wouldn't necessarily recommend it in all situations there. but certainly in terms of use on grasslands, we've seen no problems. Now, I mean, some of the issues around some of the protected urea products may be that they are being, that the agrotame is being coated locally. The urea is being bought in, it's being coated, and depending on the solvent that's being used to coat the agrotame on, you may or may not. I think there was a couple of cases maybe where some of the fertilizer was sticking to the tins on the spreader. But in general, and we use it on our farms in Johnstown and in Moore Park, we haven't seen any problem with it.
So there might be some initial quality variations there that
there may be some quality variations from manufacturer to manufacturer.
Okay, Gary, look, the time has run out on us. Thank you for your time today and a really excellent presentation. We've had lots of questions in from our viewers today that we haven't had a chance to get to all of them. So we may get the opportunity at a later stage to address some of those. And those, please, anybody who's listening, your questions aren't being put in a drawer. They will be. We will be looking at those questions and seeing how can we actually develop maybe a further webinar to address some of them. Just before we sign off, just want to show you that there is a whole list of additional webinars coming up in May. Next week, I'll be speaking to Joe Patton on feeding management for productive ruminants, and then we'll have an industry perspective from Joe Crockett of Dairy Sustainability Ireland, and then Jack Nolan from the Department of Agriculture on the 8th of May. So you can view all of those, and also you can view the previous webinars by clicking on the links within the Teagasc website. Just go to Teagasc and look at events. Also, if you haven't done so already, you can go and visit the Teagasc Connected website, and we've just launched a new Teagasc Connected digital version. So you can avail of monthly updates from Teagasc in relation to events and upcoming training and newsletters. So just click on Join Today, and you can put in your details and insert your areas of interest that you'd like to get updates on. So with that, I'd like to again thank Gary for his time today and his excellent presentation, which will be available later on, hopefully today, to download. I also want to thank our backroom team, Andy Boland, Pat Murphy, and Yvonne Marr, and also remind you that at the end of this webinar, you'll be asked to complete a short survey. We would really appreciate any comments and feedback that you'd have, and also ideas on future webinars that you'd like to, future topics that you'd like to hear about. So with that, I'd like to thank you for listening. Stay safe, and we hope you enjoy the weekend. Thanks very much.
Thank you.